Hi guys, welcome to this revision summary video looking at topic 8 of the new GCSE, which is Fuels and Earth Science. The aim for this video is to look at all the key things that you need to revise to get yourself ready for the exam. If you want to go into more detail on any particular part, I've put a link in the top right hand corner to the playlist which goes into each section of the video in more detail. The first thing we're going to have a look at then is crude oil. So what you need to do is tell me what crude oil is and how it's made. So nice and simply, a definition: crude oil is a mixture of hydrocarbons and it's made up from dead animals and plants over millions of years. So if we have a look at what a hydrocarbon is, nice and simply, as you can see from my diagram here, it is something made up of hydrogen and carbon only. That word only is really important. For example, if I have a look at this molecule here, which is carbon attached to 3 hydrogens and a chlorine, it's got hydrogen, it's got carbon. Does it just have hydrogen and carbon? No, it's got chlorine. So it's not a hydrocarbon. So a hydrocarbon is something made out of hydrogen and carbon only. So we've said crude oil is made from dead animals and plants. They're built up in layers over millions of years and the pressure turns it into our crude oil. It's a very similar method for making natural gas, and those are both examples of non-renewable fuels. Some of the major examples: methane, that's from natural gas; petrol, kerosene and diesel, they're from crude oil, and we'll talk a little bit more about some of those when we talk about fractional distillation now. So the next section is about fractional distillation. So what you need to know is, what is fractional distillation, how does it work, and what do we get out of it? Nice and simply then, fractional distillation is separating the fractions of crude oil using boiling point. When we say fractions, we mean the different fuels, and by boiling points we're talking about a physical property. So if we have a look at a fractionating column, the first thing we need to do is take our crude oil and vaporize it. Heat it up to about 400 degrees C so everything turns into a gas. We're going to add it into our fractionating column, and our column is hotter at the bottom and cooler at the top. So what will happen is when our gas goes in there, straight away our bitumen will condense and turn back into a liquid so it can be collected. Everything else will stay as a gas. So the rest of the gases will rise and they'll go up until they fall below their boiling point. When they fall below their boiling point, they will condense and they will turn back into a liquid and can be collected off. And it goes in the order of fuel oil, diesel, kerosene, petrol, and then our gases remaining at the top. And from that you can work out that your gases have the lowest boiling point because they're gases at room temperature. What you will be asked to do is work out the properties or describe the difference in properties between different fractions in our fractionating column. So if we talk about the top of the column, we've already said it has the lowest boiling point. It's also the easiest to ignite. It has the shortest chain length, so that is the size of the molecule, the amount of carbon atoms in there. And it's also the least viscous, which means it's the runniest. So if they asked you to compare petrol to diesel, and you know petrol's up near the top, you would say that has the lowest boiling point out of the two. It's the easiest to ignite out of the two. It has the shortest chain length out of the two, and it's the runniest, the least viscous. The last thing you need to know on fractional distillation is the uses. So nice and simply, gases are used in domestic heating and cooking. Petrol is used as a fuel for cars. Make sure you say the word fuel. It's not just used for cars, it's a fuel for cars. Kerosene is a fuel for aircraft. Diesel is a fuel for cars and trains. Fuel oil is a fuel for large ships and power stations. And bitumen is used for surfacing roads and roofs. This next section is going to have a look at what the term homologous series is. And there are 4 things you need to know about what a homologous series is. The key thing being they have the same general formula. They also differ by a CH2 molecule as you go up. There's a gradual variation in physical properties, and they have similar chemical properties. If we use alkanes as an example then, alkanes have the general formula CnH2n plus 2. So what that means is that if you have 1 carbon, so N is 1, you have 2 times 1 plus 2 hydrogens. So that means I have the formula CH4. If I have 2 carbons, so N is 2, I have 2 times 2 plus 2 hydrogens, C2H6, and this applies for everything. So if I had 3 carbons, it would be C3H8, and so on, as you can see from my formulas down here. Now the second property I talked about, they differ by CH2. So as I go from methane to ethane, all I'm doing is adding a CH2, which I've circled here. And the same from ethane to propane. So every time carbon goes up by 1, I get an extra CH2 molecule. The part where it says a gradual variation in physical properties, if we look at boiling points for example, as the chain length increases, so does the boiling point. So there is a gradual variation. And then finally, similar chemical properties, the alkanes all react with oxygen to form carbon dioxide and water, so they react the same way. On to the next section then, which is going to have a look at complete and incomplete combustion. Nice and simply, the difference between complete and incomplete combustion is complete combustion has lots of oxygen, incomplete combustion doesn't get enough. So if you have complete combustion, your fuel reacts with oxygen to make carbon dioxide and water vapour. If you have incomplete combustion, similar thing happens, it reacts with oxygen, but because there's not enough oxygen, you get different things. You get carbon monoxide, CO. You get carbon or soot, which is C. You can still get carbon dioxide, and you always get water, H2O. Now you'll usually be told this in an exam question, but they might turn around to you and say, what is produced by incomplete combustion? So carbon monoxide and soot are the key things. Now you will be expected to write balanced equations for complete and incomplete combustion. So we're going to have a look at a complete one, which is asking for the complete combustion of ethane, C2H6. So it's given you ethane in the actual question, so we know that's C2H6, I can put that in. And it's reacting with oxygen because it's complete combustion. The second you see complete combustion, you put plus O2. Also, complete combustion tells you you have CO2 and H2O. That's the same for any complete combustion reaction. Then all you need to do is balance it. So you work out what you've got on either side. I've got 2 carbons, 6 hydrogens and 2 oxygens on the left. 1 carbon, 2 hydrogens and 2 plus 1, which is 3 oxygens on the right. So what you need to do is choose something to balance. Now, I'm going to go with hydrogen because that's one of the easier things to look at the moment. And I'm going to times it by 3. So that's going to give me my 6 hydrogens, which makes it balanced. However, that also times my oxygen by 3. So you can see this 1 here, that's times by 3, giving me 5 oxygens on the right hand side. The next thing I'm going to look at is carbon. I've got 2 on the left and 1 on the right, so I'll put a 2 in front of my CO2. That gives me 2 carbons, so that's great. But again, it also doubles my oxygen, so I change that to a 4, giving me 7 in total. Now I've run into a bit of a problem. I need how many oxygens to get 7? 3.5. Now you can't put 3.5 in because it's not a whole number. So what I'm going to do is I'm going to double everything because that will put that up to 7. I had 2 CO2, so I'm going to make that 4. And I had 3 H2O, so I'm going to make that 6. And then I only had 1 C2H6, so I'm going to double that as well, so I'm going to put a 2 in front of that. So it will end up looking like 2 C2H6 plus 7 O2 goes to 4 CO2 plus 6 H2O. Now it's always a good idea to check this afterwards, so let's have a look. I have 2 C2s, so that gives me 4 carbons on the left, 2 H6s, so that's 12 hydrogens, and 7 O2s, that's 14 oxygens. On the right, 4 times 1 is 4 carbons. I'll look at my hydrogens next. 6 times 2 is 12. And then let's move on to oxygen. In my CO2, I have 2 oxygens. I'm timesing that by 4, so that becomes 8. And then my H2O, I have 6 times 1, which is 6. I add my 8 and my 6 together, and I get 14, which means I'm balanced. If we have a look at an incomplete combustion example, so what is the balanced equation for the incomplete combustion of methane to produce carbon monoxide and water vapour? And it will tell you in the question that methane is CH4. So straight away we put in CH4, it's combustion, so we're adding it to O2. And carbon monoxide you just need to learn is CO, and water vapour you should know H2O. So that's going to get you most of the marks in this question. Then all we need to do is balance it. So count up again. 1 carbon, 4 hydrogen and 2 oxygen on the left. 1 carbon, 2 hydrogen and 1 plus 1 equals 2 oxygens on the right. Again, choose something to balance. It doesn't matter. I'm going to go with my H's, so I'm going to times that by 2 to get my 4. That also times my oxygen by 2, so I have 3 oxygens on the right. So straight away, I'm running into a bit of an issue. But we can solve it. So a good idea is let's make our oxygens an even number. So that's my 1 over here, and I'm going to put a 2 in front of my carbon monoxide to make it even. So let's recount. That changes my carbons to 2, and the oxygen from my carbon monoxide to 2, giving me 4 oxygens on the right. I can then choose something that's not balanced on the left-hand side, so I'm going to go with my carbon, and I'm going to times that by 2. So I need 2 because I've got 2 on the right, put a 2 in front of it, that gives me 2 carbons, which is now balanced, but my hydrogen goes up to 8. Now you might be thinking, where do I go from here? Don't worry if you get to this situation, just keep working with it, keep playing around until you get it balanced. So I have 8 hydrogens on the left, and because I've doubled my water, I only have 4. So what can I times that by? Another 2. So times it by 2 again. In other words, have 4 H2Os. Then recount. So 4 times 2 is 8 hydrogens, so that's balanced. 4 times by my 1 hydrogen is 4. So therefore I now have 6 oxygens on the right hand side. So all I need to do is times my oxygen on the left by 3, and it becomes balanced. Again, don't worry if you're struggling with this, have a look at my skills section on my website, it will help you out. So we've now talked about how you can write word equations and balanced equations for combustion. We now need to talk about the dangers of incomplete combustion. And there are 2 major ones, which are the products that are different to complete combustion: soot and carbon monoxide. If we start off with soot, that's the easy one. It blackens buildings so they don't look as nice, and it also can cause cancer. It's carcinogenic. The main thing you're going to be asked on though is carbon monoxide. And the key thing is that carbon monoxide is colourless, so you can't see it, it's odourless, so you can't smell it, and it's toxic, which means it's poisonous. And what you need to know is why. So if we have a look at some red blood cells, we breathe in normally, but if we breathe in carbon monoxide, by mistake, carbon monoxide attaches itself to the red blood cells, and in particular it binds with the hemoglobin. The hemoglobin is a red pigment found in blood. So it gets stuck in there. Now eventually it'll get to the point where oxygen can't get in, or certainly there'll be less oxygen in the blood. If the oxygen can't get to the cells, respiration can't occur, and respiration is how we get our energy. So our cells are going to have less energy, and if they have less energy, that can lead to headaches, tiredness, and eventually it can lead to death. Right, the next section of this video is going to focus on acid rain, how it forms and the effects of it. So if we take any fossil fuel and heat it, a lot of our fossil fuels have an impurity, which is called sulfur. An impurity is something that shouldn't be there, something that we don't want to be there. And because we're heating that as well, it will react with the oxygen in the air and form something called sulfur dioxide, SO2. That sulfur dioxide will then rise up and it will move into our clouds. And when it dissolves in the water, it forms something called sulfurous acid. So you get a simple equation of SO2 plus H2O goes to H2SO3. That H2SO3 being sulfurous acid. That sulfurous acid then reacts with the oxygen again, and it turns into sulfuric acid. So H2SO3 plus O2 becomes H2SO4, and that H2SO4, that sulfuric acid, is our acid rain. So why is that a bad thing? So you need to remember a few different things. It acidifies our soil, it acidifies lakes or water, and it weathers statues and corrodes metal. If we go into a bit more detail on that, when it acidifies the soil, it means the plants can't grow, they can't get the nutrients, they can't photosynthesize, so they stop growing. If it acidifies the water, the pH goes too low, so animals and plants can die from it. When it weathers your statues, it's particularly your limestone statues, calcium carbonate, and when it corrodes metals, in particular your iron. And it's not just sulfur that can cause acid rain, it's also nitrogen. Nitrogen, which makes up 78% of our air. So in our car exhausts, if they get too hot, the nitrogen, N2, can react with oxygen in the air, which is O2, and it will form various nitrous oxides. So for example, NO2, N2O5, and so on. Now these nitrous oxides go up into the air again, and they can form acid rain. And this time it's HNO3, nitric acid. These have exactly the same effect that we just talked about on your statues, on your soil, on your water. There are other problems though. NO2 can cause breathing problems such as bronchitis. They can also cause smog in the air. So what we have to do to make sure that it's safe is we have to use catalytic converters. Catalytic converters go into our car, we've talked about them in a previous video, and they take those nitrous oxides and they turn them back into nitrogen. The next section of this video is going to have a look at catalytic cracking, which is nice and simply breaking down of long-chained hydrocarbons into shorter-chained hydrocarbons. Why do we need to do that though? So let's have a look at my decane here, which has got the formula C10H22. Now, we have a large supply of our large-chained alkanes, our large-chained hydrocarbons, but we don't have as much demand for them, so we don't need them as much. But the smaller ones, like C2H4, ethene, we have more demand than supply. We don't have enough of them. So what we have to do is catalytic cracking. So we heat our decane, we put pressure on it, and we use a catalyst, the heat being 650 degrees, catalyst being aluminium oxide, and it breaks those long-chained alkanes, long-chained hydrocarbons, down into shorter-chained ones. And in particular, you get a shorter-chained alkane and a shorter-chained alkene. And by doing that, we meet our demand for the shorter-chained hydrocarbons. The next section is going to have a look at using hydrogen as a fuel. Now the best way to do that is to have a look at the word equation, which is hydrogen, H2, plus oxygen, O2, goes to water, H2O. Now the massive benefit of using hydrogen as a fuel is it only produces water vapour, which means we don't get CO2 like we do with combustion of most fuels. CO2 is a greenhouse gas, and we'll talk about why that's a bad thing in a little while. So if we go back to hydrogen, it's flammable. That's a good thing because it produces energy, it gives out lots of energy. However, it also means that it needs to be stored. It's a gas, so it's hard to store. We need to have lots and lots of pressure to be able to store it, and that takes money. So that's one of your major disadvantages for using it as a fuel. And that's everything you need to know on the fuel section. So we're going to move on to the Earth and the atmosphere, starting off with the early atmosphere. So, how did our gases get into the atmosphere? Nice and simply, volcanoes. Volcanoes erupted, they gave out gases including CO2 and H2O. We're fairly sure we know this because we look at the planets Venus and Mars. Venus and Mars have volcanoes, the atmospheres are carbon dioxide. So what happened to the water vapour? Nice and simply, the Earth cooled. When the Earth cooled, the water vapour condensed and it turned into our oceans. Was there any oxygen present in the early atmosphere? We don't think so. Reason for that? Volcanoes do not produce oxygen. And also, in ancient rocks, there's something called iron pyrite. Now that is something that only exists when there is no oxygen present. So we're fairly confident there was no oxygen in the early atmosphere. What about carbon dioxide? Now, in the early atmosphere, it was around 90%. Now it's less than 1%. So how has it gone down? And there are three ways you need to know. Number one, after the oceans formed, the carbon dioxide dissolved into those oceans. So the percentage went down. And then sea creatures evolved and they took in that carbon dioxide. They used it to form their shells. As they did that, the amount of carbon dioxide in the water went down, so more carbon dioxide could then be dissolved into the oceans. And then finally, plants started to evolve. You've guessed it, photosynthesis occurred. So carbon dioxide was taken in and oxygen was produced. This next section is going to have a look at the test for oxygen. Which, nice and simply, you take a splint, you set it on fire, and then you blow it out so it is still glowing. So still red around the edges, still got some energy left. You take that glowing splint, which is your first mark, you put it into a test tube or a beaker or a container with oxygen in, and it will relight. So your test for oxygen is it relights a glowing splint. The final section of this video is going to have a look at the greenhouse effect. So the sun gives out light and heat, and those light and heat rays travel to the Earth. The heat is absorbed by the atmosphere, and the atmosphere contains greenhouse gases: carbon dioxide, water vapour, and methane, CH4. Now, if you increase the amount of those greenhouse gases, the more greenhouse gases there are, the more heat gets trapped. Now, greenhouse gases are a good thing because they keep the Earth warm enough for us to survive on it, but the more there are, it's going to do things like melting our ice caps. And if that happens, the sea levels are going to rise. That's going to lead to more flooding. There's going to be more extreme weather like drought, storms, floods. So it's really important that we do things to stop the amount of greenhouse gases going up. Now, it's really important as scientists that we can back up these claims. So how do we have the evidence that as carbon dioxide levels are going up, so is the temperature of the Earth? And this is called a causal link. A causal link is where something directly impacts on another. So what scientists did was they measured the heat or infrared energy leaving the Earth's atmosphere. And as carbon dioxide levels have gone up, the amount of infrared energy leaving has gone down. So that proves that as carbon dioxide levels have gone up, the average temperature has gone up, and we're fairly confident that there is a causal link there. You might also be asked how we're putting more greenhouse gases into the atmosphere. Nice and simply, farming increases the amount of methane, mining, fuels or ores increases the amount of CO2 and H2O produced, and combustion, CO2 given out. That is everything you need to know for this video and for the Fuels on Earth topic. Hopefully you found it useful, hopefully it's going to help you prepare for your exams, and good luck! Hi guys, thanks for watching. If you enjoyed the video, please click on like down below. You can also subscribe to my channel, you can check out the latest video, and you can visit my website up above here. Bye now.